Today we are going to learn about covalent dot structures, and you can see some examples below here. They're a little bit different than ionic dot structures, so let's compare. What we've learned to do before is ionic dot structures. That's where you have a metal and a non-metal element bonding together. So for example, we could have sodium and chlorine. And the metal, you'll remember, donated an electron to the non-metal. So because we had neutral atoms and now electrons are moving, we have charged atoms, which are called ions, so we put these brackets around them. We're also going to put the charges, sometimes called the oxidation states, in the top right here. Now, covalent compounds, the stuff we're learning about now in this video, are two nonmetals. So for example, we could have fluorine and fluorine together. Now, unlike the ionic compounds where we had a transfer of electrons from the metal to the nonmetal, a covalent compound is just going to share electrons. So we're going to show that a little bit differently. We're not going to have any ions, we don't need any brackets, we don't need any charges. But the basic idea is the same. Atoms are trying to satisfy the octet rule. They want to have full orbitals, full valence shells, because that makes them more stable. It's a lower energy configuration. So for example, we can see we've got a couple fluorines here. Each has 7 valence electrons when it starts, and they're one short of that octet they need to be stable. But they're each going to kind of put one of their 7 electrons in the middle, so it's kind of like both atoms have that electron. They're sharing it. So when you start counting that, they each end up having 8 valence electrons, and they're stable with that octet. An exception to that octet rule is hydrogen. It's a very small atom with only 1 valence electron, so it just needs 2 electrons total to be stable. But again, that's still a full valence shell for hydrogen. That first ring, that first orbital, has its 2 electrons. It's full, so hydrogen is stable with 2. Now, sharing just 2 electrons between your nonmetals is going to be your most common arrangement. That's called a single bond. But there are other kinds of covalent bonds as well. You can have single, double, or triple bonds, depending on how many electrons had to be shared to get your octet. 2 oxygens, for example, need to share 4 electrons, and 2 nitrogens need to share 6 electrons. So we've got a single pair, a double pair, and a triple pair of shared electrons, hence the names single, double, and triple bond. Now, when we have all these unshared electrons and shared electrons, things get a little bit confusing, so we generally show those shared electrons as a line. Each line represents 2 electrons. So if I have 4 electrons, that's going to be 2 lines. In other words, for nitrogen, 3 pairs of electrons means 3 lines. Single bonds tend to be pretty long. Those atoms are far apart. And as you share more and more electrons, the bonds get shorter and shorter. So these nitrogens are pretty close together. There's also a difference in strength. Single bonds, only 2 shared electrons, those are pretty weak, pretty easy to split apart. But as you share more and more electrons, it gets harder and harder to rip all of those pairs of electrons away from each other, and that's a much stronger bond. So triple bonds are the strongest kind of covalent bond. Now, our objective for covalent bonding is to be able to draw a picture of a covalent molecule. So how do these nonmetal atoms combine to make a molecule? So let's start off with carbon tetrachloride here. And carbon tetrachloride is carbon. So I'm going to put a C here for my formula. And tetrachloride looks intimidating, but just ignore tetra for a second. We've got chloride. That's going to be chlorine. Tetra is just a prefix used in the naming of covalent compounds. That means 4. So I have 4 chlorines. We're going to learn a little bit more about the naming of covalent compounds later on. For right now, let's just start with our formula and follow these 3 steps at the top here to draw a dot structure, to draw a picture of this molecule. Now, The first element in your formula is usually going to go in the center of your molecule, and we're going to draw valence electrons in all of them, just like we did when we first learned what a dot structure was. So carbon is going to go in our center because that's our first element, and it has 4 valence electrons because it's in group 14. You'll remember the number of valence electrons you get from the group number, and you're just taking the last digit. So group 14 has 4 valence electrons. Chlorine is a halogen in group 17, so each of these chlorines is going to have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Now notice I put each chlorine on either the top, left, bottom, or right. Just make things a little bit neater if you keep it in those positions. And notice each chlorine I've drawn a little bit differently. I've drawn the unpaired electrons facing the center, and that just makes things a little bit easier for my second step where I'm actually forming bonds. So right now I've drawn 5 separate atoms. I want to show how these are bonded together to form a molecule, to form something a little bit bigger. So the way I'm going to represent a bond is by replacing these 2 unshared electrons with a line. So I'm showing that these 2 electrons now are shared. Okay, notice that I'm kind of covering up the dots. I want them to be gone. I don't want you to see them because otherwise it's going to look like I have a dot and a line, and maybe there's 3 shared electrons. It gets a little bit confusing. So make sure you're really connecting those dots and replacing those 2 dots with a line to show that they are now shared. Okay, sometimes I may have to form more bonds. So before I put my final answer down, I need to check, does everyone have their octet? So the chlorines all seem to have 6 electrons to themselves and 2 electrons that they're sharing. So 3 lone pairs and 1 bonded pair. So that's a total of 8 electrons for each, and they have their octet. They're stable. Carbon in the middle has no lone pairs, no dots, no unshared electrons, but it does have 4 bonds. 1, 2, 3, 4. And each of those single bonds represents 2 shared electrons for a total of 8. So it looks like everyone has their octet, so we're ready to draw our final answer. And the reason I'm redrawing this is because, if you're working, you're probably going to have to erase a lot. You're probably going to do a lot of crossouts if you're working in pen. Maybe you've got these weird lines that are kind of in weird directions, curving around above or below the elements. A correct covalent dot structure needs to have straight lines between each element to represent the bonds. Okay. So that would be a great finished dot structure here. Okay. So let's try one more example. Let's try an oxygen molecule. This is a really common molecule. It's in the air you're breathing right now, and it consists of 2 oxygens. In step 1, we're supposed to put the first element in the center. We only have 1 element, and there's only 2 atoms, so it doesn't really matter. There's no center to this, so we're just going to draw our 2 oxygens and put on the valence electrons. You'll remember we need to put the valence electrons so that the unpaired ones are facing the center. So oxygen is in group 16. It has 6 valence electrons, so we're going to have 2 unpaired electrons. Step 2, I'm going to form my bonds between them. And then step 3, check to make sure everyone has an octet. Now I see that that oxygen has 5 electrons to itself and 2 electrons that are shared. That's only 7 total valence electrons. That's not stable. It doesn't have its octet. So oxygen is going to form a second bond. So I'm going to connect these 2 electrons with a line. And now I can see that each of my oxygens has an octet. It's got these 2 pairs of shared electrons and 2 pairs of unshared electrons. 2 lone pairs, 2 bonded pairs. So that each oxygen has 8. Now you can see this is not a very neat dot structure. I would not want to put this as my final answer. I've got this weird line like below them. They're all kind of diagonally. So I'm going to try and redraw that so that each oxygen is nice and neat, and that those bonds are straight between the 2 elements. They're horizontal. They're very neat. I'm going to check to make sure I didn't drop any electrons. Make sure everyone still has their octets, and it looks like they do, so this would be a great finished dot structure. So that's the basic idea. Go and try some of those on your own, experiment a little bit, and you should pick it up pretty quick. Just make sure you work as many practice problems as you can. Thanks.